Today we will be doing work and energy. In your lower classes, class 9 and class 10, you have seen these two formulas. Kinetic energy equal to half mv square. Potential energy equal to mgh. You have seen these two formulas in your lower classes. Now, whenever there is a force, the work done by the force is given by the dot product of force and displacement. That is the definition of work done. So work done by a force dW is equal to F dot dr. This is the definition of work done by a force. Now you know that according to chain rule, force can be written like this. Force can be written as mv into dv by dr. So basically F dot dr becomes m into v into dv by dr dot dr. Now in this expression you will see that there are two vectors, vector v and vector dr, which will always be in the same direction, because if a particle is undergoing a displacement, the direction of velocity has to be the same as the direction of displacement. So v dot dr can be simply written as v into dr, or you could say modulus of velocity into modulus of dr. So this gives mv dv. So the work done by the force is m into v dv. Now the total work done by the force while undergoing a change in velocity from v1 to v2 is equal to half m into v2 square minus v1 square. So once again, the work done by the force is dw equal to mv dv, and the total work done by the force while undergoing a change in velocity from v1 to v2 is half m into v2 square minus v1 square. Now from your knowledge of kinetic energy, you know that this is equal to change in kinetic energy. Now whatever we have established is actually a theorem. This theorem is called work energy theorem, and perhaps you have been introduced to this theorem in lower classes, but now we will formally understand what this theorem says. So you have a system and the total force on that system is F. So the work done by that force F will be equal to the change in kinetic energy. So work energy theorem states that the total work done by all the forces acting on a system is equal to the change in kinetic energy of the system. That is work energy theorem. Now in the statement of the theorem, we have used a phrase total work done by all the forces. So it is very important to understand what are the different types of forces that can act on a system. The forces that can act on a system can be broadly classified as external, internal conservative, and internal non-conservative. So these are the three types of forces that can act on a system: external, internal conservative, internal non-conservative. These are the three types of forces. What do we mean by external? External, as the name suggests, it is the force which is acting externally on the system. For example, if this is a box and I am trying to make this box move, suppose this is a box and I am trying to make this box move, then I will have to exert a force on the box. So this force will become external force. Second thing is internal conservative force. If you take a ball and throw it up in the air, then after some time the ball will come back to the ground. During its journey, that means while the ball was going up and while it was coming down, during its entire journey, the total work done by gravity is zero. As you know, the journey of the ball can be called one round trip. So the total journey of the ball up and down, the total journey of the ball, work done by gravity is zero. So gravity is an internal conservative force. Another internal conservative force is electrostatic force. Electrostatic force you will learn in detail when you go to class 12. Basically, it's a force between charges. For example, in an atom, electron is being attracted to the nucleus. That is an example of electrostatic force. The third one is spring force. Now, spring force we have not discussed previously. Spring force is basically the restoring force in a spring when it is either elongated or compressed. Let's take one example. If you have a spring which is in its natural length, now the spring has got extended by a distance x. So this is a spring which is in the natural length, and now the spring has got extended by a distance x. Now, since the spring has got extended by a distance x, a restoring force will act on the spring and it will try to make it come back to its natural length. This restoring force, if I call it as F, you can see from the diagram, this restoring force will act opposite to the displacement. So I have elongated the spring, the restoring force will try to bring it back to its original state. So the restoring force F will be oppositely directed to the elongation. At the same time, it will be proportional to the elongation. So if the elongation is x, the restoring force will be proportional to x. The constant of proportionality K is called the spring constant. So K is called the spring constant of the spring. It is an intrinsic property of the spring. Unless the physical conditions change, like you hammer it or cut it into pieces, the spring constant of a spring is an intrinsic property. It remains a constant for that particular spring. So whenever you elongate it by a distance x, the restoring force tries to restore it back to its original length, and likewise if you compress it. As you can see, the spring force is measured in Newton per meter, because force is measured in Newton and displacement of the spring is measured in meter. So internal conservative forces, you can write down the definition. Internal conservative forces are those internal forces for which the work done in one round trip is always zero. So these are the examples: gravity, electrostatic force and spring force. What about internal non-conservative forces? Internal non-conservative forces example is friction. Like let's say you are talking about one round trip. Let's say there is a room and a boy walks from one wall to the other, and after that he walks back to the same wall. So this boy starts from this wall, walks up to that wall, and then comes back. So this is a round trip. He goes to this wall and comes back. So this is one round trip. So during this one round trip, the work done by friction will not be zero. So internal non-conservative forces are those forces for which work done in one round trip is not equal to zero. So this boy goes to the wall and comes back. It is one round trip, but during his journey, the work done by friction will not be zero. So we can now try to get a broader understanding of work energy theorem. Suppose WEXT is work done by external forces. Suppose WNC is work done by non-conservative internal forces. And suppose WC is work done by conservative internal forces. Once again, WEXT is work done by external forces, WNC work done by non-conservative internal forces, and WC is work done by conservative internal forces. So the total of these will be equal to the change in kinetic energy. So now we have a much better understanding of work energy theorem in terms of all the forces that are acting on the system. The total work done by external forces plus non-conservative internal forces plus conservative internal forces is equal to change in kinetic energy. Now, when you were in class 9 and 10, you have studied that potential energy is equal to mgh. Now, we have been talking about conservative internal forces in the last few minutes. And we have also spoken about non-conservative internal forces. Now the thing is, internal forces, how are they different from external forces? In external forces, the action and reaction are not confined to the system. For example, if you are pushing this block, then the force on the block is F, and whoever is giving this push, the force on that person will be equal and opposite F. But the force on that person is not a part of this system. So on the system, F is an external force. On the other hand, suppose let us say there are two blocks touching each other and you push them like this. Now if you draw a free body diagram, you will see that these two blocks are exerting equal and opposite force on each other, F1, F1. These two forces, F1, F1, they are internal forces and together they form an action-reaction pair. So the difference between external forces and internal forces is that in external forces, the reaction force is not part of the system, and in case of internal forces, the action-reaction is confined to the system. So if you consider the total system, then the sum total of all the internal forces will always be zero if you consider the entire system. Now coming to potential energy, when you were in class 9 and 10, you were told that potential energy is equal to mgh. Now what was the basis of this? You were told that if a body is on the surface of the earth and now it has been raised by a height h, so thanks to that the body will acquire a potential energy equal to mgh. Now in this formula mgh, it was assumed that when the body is on the surface of the earth, the potential energy is zero. So if you consider surface of the earth as zero potential energy, then automatically at this height the potential energy becomes mgh. But is that a valid premise? How do you say that potential energy for surface of the earth is zero? Moreover, this is a very restrictive definition because we are only talking about potential energy of a body near the surface of the earth. So what is the definition of potential energy? Well, like you saw in this discussion, that the definition of potential energy depends very heavily on the reference potential energy, that means the zero potential energy. Like in this diagram, Earth is taken as zero potential energy. So the change in potential energy is what we will define. The change in potential energy of a system is the negative of work done by all the internal conservative forces, right? So this is a very, very important thing we have learned today, that whenever there are internal conservative forces acting in a system, the negative of the work done by all of them is equal to change in potential energy. So the interesting thing is that we are able to define the change in potential energy, but we are not talking about the potential energy definition in absolute terms, because for that we need to know what is the zero potential or what is the reference value. So the change in potential energy is negative of work done by all the internal conservative forces. So you could say that UF minus UI is equal to you have seen few minutes ago that work done by internal conservative forces, we are calling it as WC. So UF minus UI will be equal to minus in F dot dr from I to F, that is equal to WC. Now the thing is, in this equal to minus WC. In this particular discussion, we can now come back to this original equation and say WEXT plus WNC minus UF minus UI equal to KF minus KI. So what I have done is I have removed WC and written minus of UF minus UI. So we can now say that WEXT plus WNC is KF plus UF minus KI plus UI. So what we have done is that now we have written one expression, the initial sum of kinetic and potential, final sum of kinetic and potential. Incidentally, this sum is called mechanical energy. So we can say that the final mechanical energy minus the initial mechanical energy minus the initial mechanical energy is equal to work done by external forces plus work done by non-conservative internal forces. Now the thing is that suppose if I call this as MF minus MI. Now the thing is that in a particular situation, let us say there are no external forces at all. So the work done by external forces will be zero. Let us say there are no non-conservative internal forces, so work done by them is zero. So the final mechanical energy will be equal to the initial mechanical energy. So this is known as law of conservation of mechanical energy. So you can just note down the law. The law of conservation of mechanical energy states that if no external forces are acting on a system and all the internal forces are conservative in nature, then the mechanical energy of the system is conserved. So initial mechanical energy will be equal to final mechanical energy. Like say for example, when you were in class 9 and 10, there was this famous experiment that if you throw a ball up in the air, when it is at the greatest height, it will have potential energy. and when it is at the bottommost position it will have kinetic energy, and at any intermediate height the energy will be the sum of potential and kinetic. So throughout the journey of this ball, the energy may be purely potential, purely kinetic, or sum of potential and kinetic. Irrespective of that, the total energy will be a constant. So suppose if the total energy of this ball is E, then each of these will be equal to E. And now you can understand how this happened, because when the ball is making its journey, there are no external forces, because the ball is traveling only under the influence of gravity, which is an internal conservative force. Secondly, if you disregard air resistance, etc., then there are no internal non-conservative forces. So mechanical energy of the ball is conserved. So throughout the journey, the mechanical energy of the ball is always equal to E, right? Another thing which I wanted to tell you is the definition of change in potential energy which we learned just now. We can use this definition to understand how the formula mgh came about. See, if you throw a ball up in the air and the ball reaches a maximum height of h, then during the journey of the ball, the force, the gravitational force on the ball is mg, which will act downwards. So the work done by gravitational force will be minus mgh, because the weight will point downwards whereas the displacement is upwards. So if you put a negative sign in front of this, then you will see that the change in potential energy is mgh, and in absolute terms, if we take the surface of the earth as zero potential, then the potential energy of the ball is mgh. So you can see how the formula mgh is a direct conclusion of the definition of change in potential energy. We spoke about one new force which we learned today, that is spring force. Now, like I said, if you extend a spring by a distance x, then as a result of this a restoring force will be developed within the spring. This restoring force will oppose the motion of the spring. Like a spring is elongating, it will try to make it come back. So the restoring force will be minus kx. Now the thing is, the work done by the restoring force will be minus kx into dx, and the negative of this will be kx into dx. So dw will be minus kx into dx because the force and displacement are oppositely directed, and du will be minus dw, that is kx into dx. Now in this particular scenario, it is easy to understand what is the reference value of potential energy. Obviously it will be the natural length of the spring. When the spring is at its natural length, that time the potential energy will be zero. So if you elongate or extend it by a distance x, then the potential energy acquired by the spring, as you can see, integration 0 to x kx dx, it will be half kx square. So in this case, the reference potential energy is corresponds to the natural length of the spring, and if you either elongate it or compress it, then the potential energy will become half kx square. So this was a discussion about work energy theorem, what are the different types of forces, and what is potential energy, and what is conservation of mechanical energy, and finally potential energy of a spring. Now what we will do is that we will discuss another aspect of this chapter, that is known as collisions. let's say there are two bodies, that is A and B, and they are about to collide with each other, and their initial velocities are UA and UB, and final velocities are VA and VB. So the initial velocities are UA and UB, final velocities are VA and VB. Now when these two bodies undergo collision, they will exert equal and opposite force on each other. So the contact force between these two bodies will form an action-reaction pair. Now the thing is that the force on, let us say, this body will be MA into VA minus UA by T, and the force on this body will be MB into VB minus UB by T, and these two forces will be equal and opposite. So T is the time of impact. So MA into VA minus UA is change in momentum of this body. So if you divide it by time, you get the force on this body. MB into VB minus UB by T is the change in momentum of this body. So these two forces will be equal and opposite because they are contact forces, so they will form an action-reaction pair. So this will be equal to negative of this. Now if you cancel T, you will get MA into UA plus MB into UB is equal to MA into VA plus MB into VB. So the initial momentum of these two together is this, and the final momentum is this. So the initial momentum and final momentum are equal, or you could say that if you consider these two as a system, then the momentum of the system is conserved. Now this is actually known as law of conservation of linear momentum. So what is exactly the law and what is its statement? So you can note it down. The law of conservation of linear momentum states that in the absence of external forces, the linear momentum of a system is conserved. So you can see there are no external forces acting on these two. The only forces between them are internal, and therefore the momentum of the system is conserved. The initial momentum is equal to the final momentum. Now we are specifically talking about collisions, and what we will do is, to make matters simple, we will talk primarily about one-dimensional collisions. For two-dimensional collisions, you can either introduce vectors, or you can do one thing, you can analyze the two dimensions separately. So principally we will be talking about one-dimensional collisions. So to keep it simple, we will not use vector notation. We will say that if these are the two bodies, their initial velocities are u1 and u2, and final velocities are v1 and v2. Now whatever we learned in the law of conservation of momentum, if we apply that over here, then initial momentum is m1 u1 plus m2 u2, and final momentum is m1 v1 plus m2 v2. So this is the initial momentum, this is the final momentum. Now when these two bodies collide with each other, you have to understand that they are going to collide with each other. When they collide with each other, suppose these two bodies are colliding with each other, at the surface of contact there is a possibility of deformation. They may deform each other. Now that deformation, it may last only as long as the collision. In other words, it may be completely restored. Maybe just after the collision, the deformation will be completely restored and the bodies will come back to normal. So that type of collision is called perfectly elastic collision. So what exactly is a perfectly elastic collision? it is a special kind of collision in which the two bodies undergo temporary elastic deformation, which is completely restored after the collision is over. So in case of perfectly elastic collision, the deformation of the two colliding bodies, it creates elastic potential energy within them, but because the deformation lasts only as long as the collision, that elastic potential energy is completely recovered and converted back to kinetic energy. So we can say that kinetic energy is conserved. That means initial kinetic energy equal to final kinetic energy. Right? So initial kinetic energy half m1 u1 square plus half m2 u2 square equal to final kinetic energy half m1 v1 square plus half m2 v2 square. Kinetic energy is conserved. Now this conservation of momentum equation can be rewritten like this. And the conservation of kinetic energy equation can be rewritten like this. So the conservation of momentum equation can also be written like this. Conservation of kinetic energy equation can be written like this. Now the thing is that if you divide these two equations, if you divide the second equation by the first equation, you will get u1 plus v1 equal to v2 plus u2. So you can say that u1 minus u2 is equal to v2 minus v1. So that means velocity of approach is equal to velocity of separation. So this is another formula that is derived from the concept of perfectly elastic collision. Velocity of approach u1 minus u2 is equal to velocity of separation, that is v2 minus v1. So these are the primary formulas for perfectly elastic collision. Now in perfectly elastic collision, let us consider a case where the masses are equal. So if the masses are equal, we can say that m1 is equal to m2. So if m1 is equal to m2, then this equation, this one, it becomes u1 minus v1 is equal to v2 plus u2. But we have just got one equation, u1 minus u2 is v2 minus v1. So what we can do is, we can combine these two, and if we combine these two, we get u1 is equal to v2 and u2 is equal to v1. That means in case of perfectly elastic collision, if the bodies have equal mass, then after the collision velocities get interchanged. So u1 becomes v2 and u2 becomes v1. So these are the total concepts of perfectly elastic collision, that is momentum conservation, energy conservation, velocity of approach equal to velocity of separation, and if the masses are equal, then the velocities get interchanged. So these are the concepts of perfectly elastic collision. In case of perfectly inelastic collision, suppose the collision is perfectly inelastic, then what will happen is that the deformation of the colliding bodies will be permanent. They will permanently deform each other at the surface of contact. You have to understand one thing: if they perfectly deform each other, or rather permanently deform each other, then it means that they stick to each other after the collisions. So one of them is deformed in such a way that the deformation of the other fits in such a way that they stick to each other. So these deformations will remain, they will never be restored at all. So it is called perfectly inelastic collision. Without any hesitation, we can say that momentum conservation will apply, because the situation is the same as any other situation of collision, that there are two bodies which are colliding with each other and the collision forces form action-reaction pair. So momentum conservation will apply. m1 u1 plus m2 u2 is m1 plus m2 into v. Why m1 plus m2 into v? Because when they collide and stick to each other, they will have a common velocity. Let's call that common velocity as v. Now in this case, there will be a loss of kinetic energy. Loss of kinetic energy will be initial kinetic energy minus final kinetic energy. So the loss of kinetic energy, it will be initial minus final. Initial kinetic energy is half m1 u1 square plus half m2 u2 square. Final kinetic energy is half of m1 plus m2 into v square. Another thing is that velocity of separation will be zero. Why? You see, if they stick to each other, then they are not separated from each other, so then velocity of separation will be zero. So these are the important aspects of perfectly inelastic collision. Right. Now let's consider the third type of collision, that is partly elastic collision. In case of partly elastic collision, as the name suggests, the deformations of the two bodies are not completely restored, they are partly restored. So the elastic deformation remains to some extent, but to a large extent it is also restored. So what happens is that conservation of momentum will apply as always. Secondly, there will be a loss of kinetic energy. This will be the loss of kinetic energy, that is initial minus final. Another thing is that the ratio of velocity of separation to velocity of approach, v2 minus v1, if you remember, this is velocity of separation, u1 minus u2 is velocity of approach. So the ratio of velocity of separation to velocity of approach is called coefficient of restitution. So the coefficient of restitution is the ratio of velocity of separation to velocity of approach. Now this coefficient of restitution will always be between 0 to 1. If you look at perfectly elastic collision, then coefficient of restitution is 1. If you think of perfectly inelastic collision, then coefficient of restitution is 0, and in case of partly elastic collision, it is between 0 and 1. So this is how we can distinguish between the three types of collision. So perfectly elastic E is equal to 1, perfectly inelastic E is equal to 0, and partly elastic E lies between 0 to 1. So this brings us to an end of collision, and it also brings us to an end of the chapter work and energy.